Hello, welcome back. In this lecture, we will continue our discussion on greedy paradigm and will show the third example problem. This problem involves something we all do very often, and most of us do it instinctively, making change using the fewest possible coins. So the problem is, given a total value, can we make change using the fewest coins? Suppose we use Canada's coins and have a set of coin values 1, 5, 10, 25, 100, and 200 cents. We know penny was phased out in Canada, and let's assume that we still have it. If we need to make a total of $1.73, we use 1 loonie first, and then that'll leave us 73 cents. So we could use 2 quarters, and then that'll leave us with 23 cents. So we can use 2 dimes and 3 pennies. Another example is when we need to make a total of $5.34, we can use 2 toonies first and 1 loonie, and then that'll leave us with 34 cents. So we can have a quarter, then that'll leave us with, so we can have 1 nickel and 4 pennies. This, as we now recognize, is a greedy algorithm. We sort the coins based on their values, and we repeatedly use the largest coin we can. Now, this is the pseudocode of the CoinChange greedy algorithm. Suppose we have k different coin values, and we treat k as a constant. The input of the greedy algorithm, mean coin change, is m. M is a positive integer, the total value for change. We first set the remaining amount r as m. Then here is the while loop. While r is greater than 0, we find the maximum coin of value that is less than r. We select a coin of that value and update the remaining amount r. So what's the complexity of this algorithm? Sorting the coins will take big O of n log n time. And this while loop takes at most m times. So the overall complexity of this algorithm is big O of n log n plus big O of m. Before we try to prove the correctness of this greedy algorithm, let's see if this algorithm always works. In fact, not all the time. For the Canadian coins, it appears to be working. However, for cases when there's no coin with the denomination 1, for sure the algorithm won't work. Another example here is when the coin values are 9, 4, 1, for instance. Given the target value 12, the greedy algorithm will take a 9 first and will have 3 cents left. So the algorithm will take 3 1-cent coins. So we'll be using 4 coins in total. However, for the target value 12, we know that we can take 3 4-cent coins, and we only need to use 3 coins in total. So the greedy algorithm does not provide an optimal solution. There is some theoretical work on when greedy algorithms work. It turns out to be a very deep question. It has given rise to a specialized branch of mathematics called greedoid theory. This is out of the scope of this course, but here is a Wikipedia link for an introduction on this topic if you are interested in learning more. So with the Canadian coins, we know greedy works well, and now let's prove its correctness. The proof involves something we don't see all that often, multiple bases. When m is 200 or less, we treat all of them as bases. So when m is greater than or equal to 1 but less than 5, the only solution is m pennies. When m is 5, we can just use 1 nickel. When m is between 5 and 10, we can use 1 nickel and the rest of them will be pennies. When M is 10, we can select 1 dime, and so on. So we'll have a large collection of base cases. So later, you will see why we do this. Now the inductive hypothesis is that when the total amount is k and k is greater than or equal to 200, we need to prove that when the total amount is k plus 1, our greedy algorithm also provides an optimal solution. Again, we say our greedy algorithm solution is A, and it picks coins A1, A2, A3, and AT. Step 1, we need to show that solution A's first choice A1 is safe. There is an optimal solution containing A1. Step 2, we need to show that A is optimal. Now let's look at the first step. We know when k is greater than or equal to 200, our algorithm's first choice A1 must be a toonie. Suppose there is no optimal solution that contains a toonie, and we will prove by contradiction. Let's assume this optimal solution is O, which picks coins O1, O2, O3, and OR. Suppose any optimal solution O does not contain a toonie. Now let's find the contradiction. Let's find out how many coins of each value O can have at most. So for loonies, O can have at most 1 loonie, because if we have 2 loonies, we can replace those 2 coins using a toonie, and then O won't have the minimal number of coins because we can reduce the number of coins by 1. So O can have at most 1 loonie. The same idea, O can have at most 3 quarters, because if there are 4 quarters, we can just replace those 4 coins using 1 loonie. Then we'll be able to reduce the number of coins in O. But we know O is optimal, so that's not possible. So O can have at most 4 pennies, because if there are 5 pennies, we can replace those 5 coins using 1 nickel. For dimes, O can have at most 2 dimes. Otherwise, we can replace 3 dimes using 1 quarter and 1 nickel. Or O can have at most 1 dime and 1 nickel. Otherwise, if there are 2 nickels, we can replace them using 1 dime. 2 dimes and 1 nickel can be replaced by a quarter. So we can always reduce the number of coins in O if that were the case. That's all. O cannot have any more coins. Otherwise, we can always reduce the number of coins and O won't be optimal. Now let's see the maximum total value that can be achieved is 199 cents or 194 cents, which contradicts the fact that M is greater than or equal to 200. So here is our contradiction. An optimal solution must contain at least 1 toonie. That's A1, the first choice of our greedy algorithm. So now we have seen the proof of step number 1. Step number 2 of showing O is optimal will be very similar to the proofs we saw before, and you should be able to figure that out by now. In addition to completing the proof, another exercise is to have the greedy algorithm for CoinChange using American coins. It is very similar to that of using Canadian coins. Please feel free to explore. Okay, that will be all for this week. I hope you enjoyed the 3 problems for this week. We will show 2 more problems using greedy algorithms next week. Stay tuned.